All right, we're looking at infinite series, power series, Taylor series, that kind of stuff. This is question number 6 from the 2022 BC exam, AP Calc BC. This is, the part A on this one is a doozy. And then the other parts, if you know what to do, they go pretty quickly. Part D is a little tricky, so we'll get there. But we're going to start with part A. We're going to do the ratio test. And a lot of the points on part A, by the way, before it gets kind of tricky to where you got to show all the work, you can earn a lot of the points just by knowing how to set it up and kind of going through that first part. So, you know, always start it and do the best you can. And then, you know, if you're low on time, you know, move on to other parts that you can do quickly and pump out. Anyway, here's part A. We're trying to use the ratio test to find the interval of convergence. And so first thing, set up that ratio test. It's the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term. And to get those, you want to look at that general term, right? Because you can actually write this series as in sigma notation, right? It would be the summation of -1 to the n times x to the 2n plus 1 over 2n plus 1, right? That's the sigma notation for the series, and then it's just from n equals something to infinity. And to figure out where it starts, you look at that first term. It's x to the first power, and you look here and you say, okay, that's when n equals 0. That's when I get x to the first power. So that means it starts at n equals 0. All right, so that's another way to write this series, f of x equals that. So this is the general term or nth term. Same with this. That's what this is, right? So that's the nth term. So I want to do the n plus 1th term divided by the nth term. So what I'm going to do is the n plus 1th term and then times the reciprocal of the nth term. Because, you know, when you divide fractions, you multiply by the reciprocal, okay? So this is my setup, the basic idea. And so that nth term, I'll start there because I have it. This is the nth term, and I want the reciprocal of it, so I'm just going to flip it. I'm going to put the 2n plus 1 on top. I'm going to put the -1 to the n times x to the 2n plus 1 on the bottom, okay? And then for the n plus 1th term, not flipping this one, right? I'm going to have -1 to the n plus 1, and then times x to the 2 times n plus 1 plus 1. So that's x to the 2n plus 3. If you're not sure how I got there, what I'm doing is I'm plugging in n plus 1 for that n up there, right? So it's 2 times n plus 1 plus 1. And if you expand that, that's 2n plus 2 plus 1, or 2n plus 3. That's where this came from. Okay, so I'm not done yet. That's the top. On the bottom, I have 2n plus 1 also, so that's also 2n plus 3 when I plug n plus 1 in for the n, right? You put maybe parentheses around that, just so when we're multiplying together, whatever. All right, so that's the setup for my ratio test. And that right there, you want to have that like unmessed with, like a nice clean version of that ratio test in your work to start off. And you know, they've got the hybrid tests now that are delivered on the computer, and you're writing in the answer book. So that means you won't have any of this written on paper. You'll have the test booklet, and it'll just say like number 6, part A, in a big box there. And so you want to really write down this ratio test setup. You might even want to label it ratio test. But it did say like using the ratio test, so like, you know, you don't have to write that. But definitely like don't mess with this. Don't start canceling stuff out in here because there's a point for the setup, and then, you know, yeah. So go from here. So equals the limit as n approaches infinity of, and I'm going to keep the absolute values, but because they're absolute values, those -1s don't matter. Like I could redo some and think all that through, but like it doesn't matter in the end of the day because the negative terms are going to become positive anyway with the absolute value, right? Or whatever, if it's negative at the end of the day. So like we don't care about that. Again, you could cross those off because they don't matter, but don't do it in your initial work like I just said not to do, and then I did it. So I'm just going to leave them out. That's what I'm going to do. I know they don't matter. So what's left is x over 2n plus 3. I'm sorry, x to the 2n plus 3 over x to the 2n plus 1, and 2n plus 1 over 2n plus 3 as factors. So I'm just going to reduce that as I go. If you want to show an intermediate step with the negative ones gone, you can do that. But I already know, like, the x parts, I just subtract the exponents, right? Same bases, I'm dividing. So when I subtract there, I'm just going to get x to the second left on top, right? 2n plus 3 minus parentheses 2n plus 1 gives you 2. So that's just x squared on top. And then I'm going to separately put this stuff because that's really what I'm doing the limit on. That's because it's a limit as n approaches infinity. So the limit is on the n stuff. Okay, and the x is just kind of along for the ride, right? So the x squared in the absolute value kind of stays. And what I'm really looking at with this limit, because that's sort of my next thing to do here, it's the limit as n approaches infinity. I'm looking at the n stuff. And that's a linear over a linear. 2n to the first over 2n to the first. You have the plus 1 and plus 3. But when you have a rational expression like that and you're doing a limit, the limit is the ratio of lead term coefficients if they have the same degree, right? It's n to the 1, it's n to the 1. Since it's the same, we're going to take 2 over 2 as our limit, okay, which is 1. Okay, and then the x squared is still there, right? So again, just the yellow highlighted part turns into 1. The limit is done now. It's 1 times x squared. Oops, keep the same color there. So that's the absolute value of x squared. And again, that limit of, you could even write if you want. I'll just be very thorough here for the video's sake, but you don't have to write this. I'm just showing where this logic is again, because the limit as n approaches infinity of 2n plus 1 over 2n plus 3 is 2 over 2, which is 1. Okay, that's the reasoning there. Okay, so absolute value of x squared, you might also be thinking, I don't really need the absolute value. That's true. Because that x is to an even power, you don't need the absolute value. That's absolutely right on. So I have that limit. Whoops. Let's kind of move that there. Okay. When you do the ratio test, this was the setup, this is the limit. That's probably 2 points right now on the scoring rubric. Now I need to find that interval. So with the ratio test, what you do is you compare the result to 1. Right? When the ratio test, when that limit is less than 1, then we're convergent. When the limit is greater than 1, we're divergent. And when it equals 1, it's inconclusive. So when it equals 1, we're going to test the endpoints, right? So we're going to say x squared is less than 1. We want to solve this for the interior. And, I can look at this, and there's a lot of ways you can do it. Maybe you can just look at this and say x is between negative 1 and 1. You could think about it graphically. You could actually take the square root of both sides. Pre-calc teachers might cringe there, but the square root of x squared is the absolute value of x, and then the square root of 1 is 1. And so then you can get negative 1 is less than x is less than 1 from that. However you like to do it. But the pre-calcy way to do it would be to bring the 1 over to the left side and factor into a sign chart, right? So this gives us x squared minus 1 is less than 0, x plus 1, x minus 1 is less than 0. And yeah, if you do a little sign chart, whoa. 1 and negative 1 are your key numbers. And you can even list the factors, x plus 1, x minus 1, and do the rows for those. However you like to do it. That's pre-calc stuff, so I'll let you figure that out. But the whole thing, x squared minus 1, is going to be positive on the outsides of those zeros and negative on the inside. It's negative between negative 1 and 1. And that's what we want, because we wanted to know where x squared minus 1 is less than 0. That tells us where x squared is less than 1. So that's our interval that we get. That's the interior. So interior converges for negative 1 is less than x is less than 1. Okay, and that's a big part of it. That's I'm probably up to like 3 points now on the scoring rubric, would be my guess. The next part is to test the endpoints, so -1 and 1. So I'm going to do that now. And get this out of the way. So test, and I recommend, like, label this stuff, right? Let them know what you're doing. So x equals -1. That means we're actually going to plug -1. I'm trying to scroll up and I did the opposite. I'm trying to plug -1 in for x in the general term here, right? Like right in there. And so what does that give me? What does that series look like? So at that particular case, when x equals -1, is this series going to be convergent or divergent? And then the same thing at x equals +1. So I get the summation from n equals 0 to infinity of -1 to the n times -1 to the 2n plus 1 over 2n plus 1. And when I look at that, I'm going to tell you what I see, because like big picture idea here, if you can see it the way I see it, it makes it kind of easy. You know where it's going. I see a bunch of -1 stuff here that is either an alternator, that makes it an alternating series, or that like cancels out in a way so that it's not alternating. We need to figure that out, because the rest of it is 1 over 2n plus 1. And if you've done a lot of like series convergence testing, hopefully you see this and think, hey, that smells like the harmonic series, 1 over n. You could factor out the 2, and then you could do a limit comparison test, and it would work. We know that the harmonic series, 1 over n, diverges. But the alternating harmonic series, if that is an alternator, the alternating harmonic series converges. Very common with these kind of power series problems at the endpoints to have this come up, where it's either the alternating harmonic series or not alternating harmonic series, in which case, you know, that tells you whether the endpoint works or not. So that's what we need to figure out is that an alternator first and foremost? Because if it is, then it's alternating, and that means that it is, in fact, convergent. We'll do the alternating series test to prove it, if so. So I'm going to put these together. They have the same base, add the exponents. So that's -1 to the, and then n plus 2n plus 1 is -1 to the 3n plus 1. And then on the bottom I just have 2n plus 1. From 0 to infinity. And is -1 to the 3n plus 1 an alternator? That's the big question here. And it is. If it's because of the 3n, because that's an odd number in front of n. If you plug in 0 for n, you're going to get 1, right? 3n plus 1 is 1 when n is 0. But when you plug in 1, you get 4. And when you plug in 2, you get 7. And when you plug in 3, you get 10. So the point is, it goes up by 3 every time. So 1, 4, 7, 10, 13, 16, right? Each alternating term gives you an alternating between even and odd power on -1 because of that 3 on the n. So it is alternating. That's really all we needed to know to do what we're going to do next. So I'm going to say that. Oh, I keep extending, but I need to scroll. All right. So I'm going to say this is alternating. Okay? And so I'm going to do the alternating series test. The limit as n approaches infinity of the absolute value. So I can just leave off the -1 part. So 1 over 2n plus 1 is 0. And if I plug in, like basically the terms are decreasing. You could even just write out the terms of this series decrease in magnitude toward a limit of 0. That would work. Or you can show it this way. There's the limit. That's the limit of 0. And then for decreasing in magnitude, show that the 1 over 2 times n plus 1 is less than 1 over 2n plus 1. In other words, the n plus 1th term is less than the nth term for all n starting at 0, greater than or equal to 0. You can even say or equal to, this is true. So for all n greater than or equal to 0. In other words, I'm going to write it here because I think it's going to help in a minute on the other endpoint that we test. So the terms decrease in magnitude toward a limit of 0 So that is the alternating series test, and what that means is that the series does converge. At x equals -1, the left endpoint. So now the right endpoint. For the right endpoint, I'm going to plug +1 in now. And when I plug +1 in, what happens is this. When I plug 1 in for x, it doesn't matter what power that is. 1 to any power is just 1, right? -1 was a different story, but 1 to any power is 1. So what's left is just the rest of this. The -1 to the n over 2n plus 1, which is an alternating series. So let me show that. Show the setup for the series. It's -1 to the n times 1, if you want to say to the 2n plus 1, over 2n plus 1, n equals 0 to infinity. And you can say is alternating. And the terms that have the same magnitude as the terms in the one we just looked at. Now, they do have different, I think the signs are switched on all of them, but it doesn't matter, right? It is alternating, so they do switch signs every term. And as with, so I don't have to show it all again, x equals -1, the terms decrease in magnitude, because it's the same thing, right? The magnitudes are the same toward limit of 0. In other words, the series converges. For x equals 1. And so what does that mean? My final answer here, the interval of convergence, which is what was requested, is -1 to 1 with both endpoints included. That's part A. I told you that was a doozy. Proving that, you might have been able to write a little less to do it, but, and again, the right endpoint, I should have said x equals 1, right? To prove it, you don't necessarily have to write everything I wrote, but you do have to do the things that I did here. Set up, this is like 1 point here, usually the interval or the ratio test setup. Getting that limit is usually a point. Getting the interior of the convergence is usually a point. And then there might be like a point for testing the endpoints and a point for the correct conclusion. There could be up to 5 points on this, or maybe just one more point for like all of that. But that last point is tough to do. Like to get that last point, it does say justify. So you really do need to fully prove it one way or another. All right. Part B. The rest of this is going to go a lot quicker now. Part B. This is tricky. This is a little bit of a curveball. This is a alternating series error-bound question or remainder formula, however you like to call it. This right here, it looks like the alternating series remainder or error-bound, but it's a little funky because they just have 1/2 there instead of like, you know, p of 1/2 or t of 1/2, right? So like typically what you're used to if you've done a lot of these in class is f of the absolute value of f of 1/2 minus p of 1/2, or maybe t for Taylor of 1/2, p for polynomial. And often there might be a subscript there, like p2 or p3 or something. And the order can even be switched. It doesn't matter. It's the difference between them, right? The absolute difference between them. The big idea here is that polynomial, the Taylor polynomial, here I'll put a subscript n there. This is the nth degree Taylor polynomial. And all that means is we start into this series, but we stop somewhere. So like the third degree Taylor polynomial here would be the first 2 terms, right? Because that's third degree. So this would be the third here, it'd be P3 of x. P3 of x. And then the rest of this is called the remainder. And we could call that R3 of x, the remainder. And it's also called the error, because if you plug in a value like 1/2 for x, then we can approximate the entire value, f of 1/2, by using just a couple of terms, or maybe 3 terms, however many you do. And then the error is the rest of the terms, the infinitely many remaining terms, right? And it seems crazy to use just 2 terms and then call the other infinitely many an error. But they get small. Those terms get small fast. So the first terms are the biggest ones. Okay, so it actually does work pretty well. In this case, we're not even going to use 2 terms. You'll see in a second. But that's what we have to figure out. This problem is different than other ones I've seen in the past, because they don't tell you what this 1/2 is. They didn't say like the second degree Taylor polynomial. Okay, it's actually the first degree Taylor polynomial, which is the same as a tangent line approximation. And to show that, here's what we're going to do. We're just going to say f of 1/2, so like using a Taylor polynomial to approximate. I'm going to say approximately equals, and I'm going to figure out, when do I get to this value, to 1/2? Well, I get it right away, because the first term is just x. So f of 1/2 is approximately 1/2, and then I could say, you know, like minus 1/2 cubed over 3. That would be the third degree Taylor polynomial, like I was talking about here. But I don't want to do that, because f of 1/2 approximately equals 1/2. This is already the value we're comparing it to. I want to know, how good of an approximation is that if I just use the first term only? And typically, just one term is not a great approximation. You wouldn't normally stop there, but it's a simple problem. So if you recognize that, I'm going to write this down now. Okay, this is the first degree Taylor polynomial. P1 of 1/2. That's what that is. Okay, or T1 if you like T for Taylor better. All right, so how do I approximate then? Or I did approximate. How do I find the remainder? Well, in this case, I didn't use the first 2 terms. I only used the first term. So that's what I used. So the rest is all the remainder. And for a bound for the remainder, because it's an alternating series, right? Because every term changes signs, and because they do decrease in magnitude toward a limit of 0 right away, you can actually use the next term as your bound. So I can say the magnitude of this error, f of 1/2 minus 1/2, has to be less than or equal to the value of that next term. The first one I didn't use, the magnitude of that. So absolute value, and then it's just going to be, you can put the negative or leave it off because it's in an absolute value, 1/2 cubed over 3. And 1/2 cubed is 1/8. The absolute value, like I said, the negative doesn't matter. So I have 1/8 over 3, that's 1/24. And 1/24 is, that's our error bound. Well, that's less than 1/10, so we're good to go. Already did it. Okay, so again, I spent a lot of time explaining the concept here, but if you know what you're doing, this question can be super quick. You just, when am I stopping? Oh, I'm stopping on the first term. Boom, okay, it's alternating. My error bound, I love the alternating series error bound. I just use the next term's magnitude. Boom, there it is. It's less than 1/10. Done. All right, part C. Part C is pretty typical for a Taylor series problem. Like you've probably done some of these before. We're just showing f prime of x using the Taylor series here, or the infinite series, the power series, whatever. All the same thing here. F prime of x equals, and I'm just going to do the derivative of the first term, is just 1, minus, and then the derivative of the second term, 3 times x to the second power over that 3, and then plus 5x to the 4th power over 5, right? I'm just doing the power rule. Bring the 5 down, subtract 1 from the power, and the over 5 stays. Okay, and then minus 7x to the 6th over 7. It says first 4 non-zero terms, 1, 2, 3, 4, I've got that. And the general term, so plus yada, 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 plus, and this is the general term of f. So for f prime, I'm going to take the derivative. Negative 1 to the n is a constant, so leave that for any n value. And then this is x to a constant power, so we're going to do the power rule on it. 2n plus 1, bring the power down, x to the 2n plus 1 minus 1, right? So just 2n. And then over, and then 2n plus 1 on the bottom is a constant multiple again, so you just leave that. Plus dot, dot, dot. Or maybe you don't even do that work to do the power rule on this. Maybe you just simplify these and realize the pattern, because it's a pretty simple one. Let me show you. 1 minus, and then, the 3's cancel, so I just get x squared. And then the 5's cancel, so I have plus x to the 4th. And then the 7's cancel, so I have minus x to the 6th, plus dot, dot, dot. Hey, it looks like it's going up by 2 every time, so you might think, okay, that's x to the 2n. And then it is alternating, so I have negative 1, and then to the n, and then you check the alternator, and you say, okay, the first term is when n is 0, because it's x to the 0. There's no, it's a constant. And if n is 0, it is positive, and I do want the first term to be positive, so my alternator is correctly calibrated, as I like to say. If it wasn't, then we'd have to do like n plus 1 or n minus 1 or something. All right, plus dot, dot, dot. So that's the simplified form of f prime of x. And I think you want it in that form because, again, part D is a little bit of a curveball, and we're going to use this here. This is f prime of x simplified. So I'm going to copy that, and let's go to part D. All right, so on part D, find the value of f prime of 1/6. Now you might be tempted to approximate f prime of 1/6 by plugging 1/6 in and doing a few terms. And you'll get very close because this converges fast, right? 1/6 to the 6th power is very small. So you could do that and you'd be close, but you wouldn't be right. All right. What happens is this is an infinite series and it is geometric. As you go from one term to the next, it multiplies by the same thing every time. So one way to do this is just to go ahead and plug in 1/6 and see what the pattern is. 1 minus 1/6 squared. Well, here, I'll put 1 over 6 squared. It's more like how it was written. Plus, oh, I guess it is 1/6 to the, yeah, whatever. Anyway, same thing. 1 over 6 to the 4th minus 1 over 6 to the 6th, right? Plus yada, yada, yada. And it's a geometric series. It's infinite. And when you go from one term to the next, we keep multiplying by the same thing. That's what a geometric series is, right? We keep multiplying by negative 1 over 36, right? Negative 1 over 6 squared. That's how you get from one term to the next. Okay, when that happens, that infinite summation is equal to the first term, which in this case is 1, so nice and simple, over 1 minus r, that common ratio. So 1 minus negative 1/36. So this is one way to just kind of do it. That's 1 over 1 plus 1/36. That's 36 over 36 plus 1 over 36. So that's 1 over 37 over 36, or 36/37. Okay, but I'm going to show you one other way to kind of go through this because you do want to know this, because sometimes they don't ask for the value of f prime of 1/6 on a question like this. They'll just ask for an algebraic function for f prime of x. And you could kind of do it the same way. You could be like, oh yeah, common ratio is negative x squared, and use the same formula but with negative x squared there. That would work. But it's also like just thinking about it in terms of the geometric series convergence formula. And this is really a good way to know how to do this. You need to know that wherever it starts, 0, 1, it doesn't matter, but let's just start it at 0. Infinite series of a geometric series, so a times x to the n. If it converges, right, if x is between negative 1 and 1, it equals the value of the first term, which is a, because if you plug in 0 for n, so you do have to be careful and make sure that the a is like, it's not just the multiple here if it doesn't start at 0, you know? Like it's the value of the first term. okay, over 1 minus that common ratio, the x, okay? So let me get rid of my extra, whoops, what'd I do? Okay, weird. So a over 1 minus x. 1 over 1 minus x times the value of the first term, whatever that first term is. So you actually want to plug in 0 to the beginning to find it, okay? So if you do that, you just have to look at this and say, okay, what is this? Well, it's this, right? It's the summation of negative 1 to the n times x to the 2n from n equals 0 to infinity. And you can actually put that together because, here, let me put it in a darker color so it shows up on this background. X to the 2n, this is to the n power, this is to the 2n power. So let's make them the same. I can make that x to the second to the n, right? That's the same thing as x to the 2n. And so I can write this as negative x squared to the n. Oh, I should put a summation, so this is still equal. Negative x squared to the n, right? Because like negative 1 to the n times x squared to the n, you can multiply the insides and keep that power. So it's negative x squared to the n. Again, from n equals 0 to infinity. And so the this function, this is f prime of x. That's what this is, right? This function. And it's going to be equal to, when I plug in 0 for n, so that very first term, I get 1. So 1 over 1 minus, and then this common ratio, the base of the exponential function. So minus negative x squared. So that's 1 over 1 plus x squared. And that's the function. That's what f prime of x is. F prime of x is 1 over 1 plus x squared. And there's other ways you could have gotten here. Something with like arctangent, right? This is the derivative of the inverse tangent. So maybe you know that this is the inverse tangent infinite series. And you probably should, honestly. That's one of the ones you might want to memorize. And so if you know that, then, I'm sorry, not that this one is. Maybe you knew that f was the inverse tangent infinite series, right? And so then this one is the derivative of that, which is the derivative of inverse tangent, 1 over 1 plus x squared. Anyhow, if you know those, it can make it easier. And you could have used that reasoning. You could have said, well, f of x is arctangent of x, and so f prime of x is 1 over 1 plus x squared, and you get there that way. And that works. All right. Well, that's it on this one. I think I covered it pretty thoroughly here, hopefully not too pedantically. Thanks.